2 minutes to go, Grant.
Perfect. Okay, and I'm just going to get my slide deck up now then.
Yeah, absolutely.
So I'm just going to let this play for the minute 30 as described.
Hello, everybody, and welcome. There's a nice hand going up. If I could ask you to, sadly, I'd like to see the hand, but if you could actually put your cameras off, please, and keep your microphones off, that would be absolutely superb. Good afternoon, and welcome to the National Manufacturing Conference and to the afternoon workshops. Hope you've enjoyed the day so far. Today's workshop here is an introduction to additive manufacturing by the National Manufacturing Institute of Scotland, and I'm joined by Grant Payne, who will chat us through the offerings from NMIS, some of the technologies that are available for additive manufacturing, and I guess more importantly, some of the terrific case studies and applications that 3D printing, additive manufacturing can offer us, and indeed there are many. By way of kind of protocols today, once again, please, if you could keep your mics off, cameras off, after Grant has run through the session today. It'll be time for questions and answers, at which point we can open up. But in the meantime, please feel free to put any questions that you have in the chat box. And I think we are just about ready to hand over to Grant.
Excellent, thank you very much. So as Ian has described, the workshop that I'm going to deliver today is an introduction to additive manufacturing. So just a little bit of housekeeping, just to build on what was already described there. This webinar is being recorded, so if you did not consent to that, please keep your camera and microphone off for the duration of the workshop. You're still welcome to submit questions via the chat bar function. This is not being recorded. So your microphones and webcams will be turned off. Please do not try and switch them on until the questions session. That'd be fantastic, thank you. And yes, please put all your questions into the chat bar and we'll pick them up and answer them at the end. So I'm just going to quickly run over the agenda of what we're going to cover today. So brief overview of additive manufacturing, then we'll look at some applications, moving on to design for additive manufacturing, case study with a company we've been working with, a look at design for manufacture, a look at the AMBATS support packages that we offer, a bit of analysis that we've done on the Scottish manufacturing sectors and some of the opportunities we've identified in additive manufacturing, case study with another company we've been working with, RAM Engineering Limited, a look at opportunities in low carbon manufacturing with a focus again on additive manufacturing, and then looking at process suitabilities, some applications in these, again process suitability, key considerations to take away, and then we'll finish off with a Q&A session. So the main project that I'm going to be discussing today is the business and the additive manufacturing business and technology support, otherwise known as AMBATS. This is funded by EU and another body of money, and it's moderated by Scottish Enterprise, and it's part of the Advancing Manufacturing Challenge Fund portfolio projects. So NMIS is the lead research institution, and we're part of the University of Strathclyde. The principal investigator on this is Stephen Fitzpatrick, and I'm the project lead. And this project will be running until December 2022. And this workshop is part of our awareness events that we have planned. So if we look at additive manufacturing, it is actually a collection of different technologies. And then these technologies are categorized into these 7 categories here. This is part of the joint ISO ASTM board that they have on this, and the particular standard is referenced down the bottom there for you. Now, of the 7 different technologies which can process metals, ceramics, polymers, and other materials, the National Manufacturing Institute Scotland has capabilities in material jetting, material extrusion, powder bed fusion, and directed energy deposition. So these technologies all have their different advantages and disadvantages, and they have their own unique processing capabilities to them. So looking at some applications here with a focus on metallics, you can see these technologies are capable of manufacturing everything from, see at the top left there, is part of a satellite structure, to below where you have a propeller from a marine application. Beside that, you have an acetabular cup from a total hip arthroplasty surgery, where you've got a specific surface on the top that allows osseointegration, and above that you've got part of a rocket nozzle injector system, and a whole host of other applications. Looking at polymers, you have everything down from the bottom left there with bespoke manufactured hearing aids, medical training tools above, shown with the lungs there, and some kind of quite quirky and unique ones where you've got applications in animation, and then down the bottom right, high fidelity prototyping prior to moving forward with manufacturing. So you can see a broad range of different applications for the technology, from a range of kind of prototype to end use applications. When we start to think about how the technology is then used in terms of designing for the process, you can use it just to manufacture a conventionally designed component. You can quickly adapt a design for use in additive manufacturing. But where additive manufacturing's key strength lies is the ability to design with quite a bit of design freedom. And this is where we really start to talk about design for AM. So you can kind of see on the right hand side there how that kind of looks, and some of the percentage savings, just thinking about lightweighting and material savings that can be achieved with that. Now, when we start to think about and talk about design for additive manufacturing, what we're actually talking about is a range of different unique optimization methodologies and algorithms. So as I previously discussed on the slide before, the acetabular cup I've highlighted there in the biomedical one, where you can create these very fine architectures on the surface that allow the bone to grow and fuse in there, so you have a successful operation. Topology optimization, where you're playing around with the form. Level set is one of the algorithms that's happening in the background. Consolidations, where you can bring an assembly of parts into a single component. Conformal ribbing is where you can then use a strategy to strengthen and create rigidity on a component. Density-based methods are very key for lightweighting, where you can create a solid shell on the outside, and then within that have a microarchitecture that is very lightweight but still has the same strength properties. Evolutionary-based methods is another algorithm that's often happening behind the scenes. And then there's also thermal and flow, where you're able to control the heat and the flow rate of liquids and materials within. Now, what you'll find with commercial softwares is they will use a range of these and in a slightly different proprietary ways. So depending on what you are looking to do as a business, there's often a couple of software packages out there to suit you. And in some very niche circumstances, you might need to use a couple together to really achieve what it is that you're trying to do. Now, often people wonder what's the difference between design for AM and generative design. So generative design is more of a concept generation tool, where this allows you very quickly, based on your inputs that you tell the system, to generate these range of different concepts quite quickly. Again, the software can use some of these optimization strategies, methodologies, and algorithms, but as I say, it's more about creating lots of concepts very quickly. So just quickly looking at a case study from a company that we have been working with. Back 2014, AS Pro Engineering started to look at some motorsport applications, and this is a suspension arm from a touring car, and they were really looking at using some conventional manufacturing processes, in this circumstance machining. How could they strip out weight so they could deliver higher performance to the part that they were designing and manufacturing? So that you can see that first iteration there in the middle, where they managed to remove a lot of the material, but they were still constrained by the typical traditional manufacturing processes. However, their latest incarnation of this, as you can see down the bottom right there, is really starting to use some of these advanced design freedoms that I discussed. And in this circumstance, you can see the use of topology optimization and how that's enabled them to lightweight the part even further. And this is only enabled through additive manufacturing. You couldn't manufacture this by traditional means. So we're seeing a lot of this, obviously, in the high-end motorsport market. But with things like the 2030 EV regulations coming into play, it will be more and more commonplace that we see the drive for lighter weight components through advanced design, which is enabled then through advanced manufacturing coming into the general marketplace. So what's then happening with design is you'll see it's being kind of driven by these four main factors. So the design and function optimization that you've employed, the manufacturing standards, post-processing considerations such as metrology, machining, heat treatment, and then also the manufacturing limitations of the manufacturing process that you're using. So as I previously described, each of the 7 different technology families have technologies within them, and each of these technologies naturally have limitations to how they operate. So taking a closer look at the AM-BATS project itself, what we've done is we've created a number of different support packages, and this project is free to access for SMEs based in Scotland. And there's a range of different things that we're trying to help you with here. Looking firstly at things like product suitability, then assisting you with design for AM, and then moving all the way through that design process to the very end, looking at support towards approval, where we're then talking about certification, qualification, all these different aspects. But we're mindful to have a kind of eye on the prize from the very beginning in what we are doing and designing with that in mind. There's other things that we can then cover in here, such as if you wish to bring the manufacturing process in-house, how would you set up a factory cell to do that? If you follow the web link down the bottom there, you'll be able to find more information on that. But also, if you visit our stand today, there'll be there'll be material there that you can download, and it goes into more detail about these different support packages. But what we will do with them is, it's not set in stone. We will tailor everything to align to what your engineering challenge is and how your business operates. If you're not an SME based in Scotland, then we can still help you through NMIS. So it's a slightly different web link for you to follow there, and please do get in touch and we will assist you as best we can. So what we did at the first part of this project was look at what are the different manufacturing sectors within Scotland that we felt would benefit from additive manufacturing. And as you can see there's a wide range of different sectors that Scotland excels at, that we felt additive could be of benefit to them. But probably some of the most the ones that would stand to do the that would stand to do the best with additive manufacturing, we feel, are things like rail, freight, aerospace, motorsport, tool molds and dies, and medical devices. But we're open to any application and engineering challenge that you may have for us. So again, a quick case study. We've been working with RAM Engineering up in Forfar, and they are a machine reseller. And prior to working with us, they had mainly been working with traditional manufacturing processes. But now that they offer some additive manufacturing services, they've seen their sales inquiries really increase, but not only within UK and I, but worldwide. So especially Europe, Australia, Middle East and South America are some of the new markets that they're now getting sales inquiries from. And these are very diverse as well. So everything from oil and gas to sports, and from jewellery to automotive. So a really good mix of the kind of traditional larger ones, but also some of the smaller and more niche ones. So one of the big things that we're focusing on as well just now is low carbon manufacturing, and additive manufacturing offers a lot of opportunities in this. So if we were thinking about resource efficient design and manufacturing, this is where a lot of the optimization and design freedoms that I previously described come into play. So naturally, if you can manufacture something with less material, lighter, then it's going to have environmental benefits, not only in the manufacturing process, but also when it's being used in industry. Thinking about the circular economy as well, additive manufacturing can really benefit what you're doing in terms of repair, recondition, remanufacture. The technology is very well aligned to looking at existing assets that you have, and then being able to bring these back to service condition to be put back in to the supply chain. There are a lot more recycled and green materials we see being used. So in some of the manufacturing processes, what you can do is recapture, reprocess the materials you have been using so they're not waste, which is different to, say, with machining. When you create swarf, that swarf is kind of sent for recycling, and it's quite hard, or quite it's a long process chain for that to come back to a part that you might machine again. Whereas with additive manufacturing, the powders can be reprocessed very quickly and put back into use. We're also doing work looking at how we can capture materials and recycle them and then put them back into use quite quickly from different applications, so waste plastics and polymers. And the other thing that we've been seeing with additive manufacturing is the supply chains are often quite a bit greener, in the sense that they're a lot more localized in their nature. So starting to look at the process suitability just at an overview level. Often in the media, you'll see things like 3D printed houses when they start to talk about using additive manufacturing for concrete. While there's obviously the reasons and rationale why some of these companies have been looking at it, in actual fact, what might be a better use of the technology is to manufacture, say, these tetrapods that I've shown down below here, which are used for coastal erosion. And what you could do is actually set up a remote manufacturing facility to make these in situ. But also we've done some research and found that you can actually harvest marine polymer waste and then process that into your concrete mixture and then immediately capture all that waste into your coastal erosion defense system. Again, often you'll see in the media when they begin to discuss applications of additive manufacturing in space, these massive components. And again, there's the reasons and drivers behind why these people have moved forward with this process. But thinking about all these optimization strategies and benefits that you can get from the design freedoms, some of these applications that you see on the right-hand side here, where you've lightweighted the structure, you've consolidated a large assembly, and you've also played around with the form to increase things like flowability, give you such huge benefits in things like rocket engine design. And again, this is where we see probably a lot more focus should be drawn to. Another application here in marine, a lot of people have probably seen University of Maine with their 3D printed boat. Fantastic, I would quite like one myself. But again, there's probably a lot better manufacturing processes suited to making these kind of small to mid-sized boats. Whereas if you start to think about things like complex geometries with low manufacturing volumes, such as propellers, this is again where additive manufacturing kind of holds its own. These are the key kind of things that it's good at, as I say, low manufacturing volumes, complex geometries. That's a really good application of the technology. Looking at more civil engineering now, this bridge that was manufactured in Amsterdam, absolutely beautiful, but you can see already down the side here where there's that kind of ridging effect. Now the problem is, once you get up to this large scale, if you do encounter a problem in the manufacturing process, unfortunately, most often you'll need to scrap that component because you'll have problems mechanically with that part of the bridge. So instead, maybe if you focused on things like using topology optimization, lightweighting methodologies to create complex small volumes of brackets and other kind of mechanical fixings, again, would be quite a good use of the technology. And my last one is food and drink. So again, there's often this misconception that if we were going to 3D print some food, it's going to look like for like what we're used to seeing. But in actual fact, what a project Philips did quite a long time ago now, actually, down below here, where they've got these kind of food cubes with the nutrients designed exactly for the person that is going to be consumed by, is probably where that technology will end up going. And if you then start to think about this in a healthcare setting in terms of providing nutrients to poorly and sick people, again, this is where it's got real benefits, and we're starting to see the pharmaceutical industry then picking up this and looking at stratified medicine, where they're delivering dosages, again, tweaked to the person, but also with a number of different pharmaceuticals, all delivered in one kind of tablet. And the last thing I'm just going to discuss is thinking about some of the key considerations about using additive manufacturing in your business. Due to the kind of complexity of the manufacturing process, there's a lot more advanced knowledge required, both in the design, the manufacture, and also the certification, etc., that I've mentioned, which means that you'll often need dedicated expertise to do this. The supply chains, whilst greener, as I described earlier, they are quite a bit more complex or different to what you might have previously been used to working with. Understanding commercial suitability. So now thinking about, is your sector that you work in ready to accept parts that have been designed or manufactured through additive manufacturing? This is a big challenge and something key to understand before you embark on doing what you're doing, and that links into what I've got down the bottom there, certification challenges. There are a lot more standards being produced every day, every week on this. So much so that ISO and ASTM have joined up together to make the F42 committee on exactly this. So something to be mindful before you begin. As I described, the actual manufacturing process itself is quite complex, often using very fine powders, and it's using energy sources such as laser beams, electron beams, gases, vacuum chambers, and with that obviously comes the challenges in health and safety. But this is where we kind of come into this, and we kind of help you kind of break down the barriers with all the kind of complexity and the knowledge required, and signpost you to existing supply chains and different suppliers that are out there commercially already operating to get you kind of going. And that's everything from me at this moment in time. So we've got some time now allocated for questions. So Ian, do we have any there just yet?
Microphone back on. Yep, hi. Nothing there yet. So if anybody has any questions, feel free to raise your hand, put something in the chat box, and we can get round to it. But actually, I've got a couple of questions just to maybe kickstart the process, if you don't mind, Grant.
Absolutely.
Which is, thanks for a terrific introduction to additive manufacturing and the capabilities that exist within NMIS and AMBATS as organisations, and also some terrific case studies. I like the one about food and drink. Doing a bit of research myself, I understand that Hershey's have actually trialled 3D printing for chocolate, which would normally be moulded. However, just to go over the key capabilities then, what are the kind of key additive manufacturing technologies, and specifically around metal, I'm thinking, that NMIS has access to?
Yeah, good question. So thinking about powders, first of all, we have laser metal deposition with powder, which sits within the directed energy deposition family. What we actually have is that set up in a hybrid system. So we have laser metal deposition as well as machining, all in one platform that we can move between interchangeably. And what that hybrid platform allows us to do is some of the remanufacturing that I discussed earlier. So a lot of the work we've been doing is we'll bring in a die or a mold tool, and using metrology, so we can use 3D scanning. We can compare the worn or damaged die with its digital twin, so its CAD model. We can then isolate areas and pockets of wear, come in, machine them to known geometry, build that back up using additive manufacturing, and then machine finish it back to a usable state. We also have two Renishaw 500S systems. They're laser-driven metal powder bed systems. On that as well, we have one machine fitted with a reduced build volume, and this is going to be our R&D based machine. And what the RBV does is allow us to work with many different materials without having to spend days and days cleaning down the system in between moving, say, from an Inconel-based, a nickel-based alloy such as Inconel to something like a tool steel or even a titanium alloy. With the bigger, larger build volume on the other machine, the standard supplied build volume, we'll probably have a more like a workhorse machine where we're going to work with industry to identify what is the primary alloy that we should have in there day in, day out. Thinking about metal wire-based systems, we have 2 wire arc additive manufacturing systems. They sit within, again, the directed energy deposition family. One of those is a more open architecture system, and it sits within open atmosphere. And what that allows us to do is work on larger parts up to about 2.5 meters, with one KUKA robot dedicated to doing the actual additive manufacturing itself, and another robot dedicated to doing NDT, so non-destructive testing on that. These are obviously for our larger build volume capability, so building big parts quickly. The other machine sits actually within an inert atmosphere, so within an argon atmosphere, and this only now has one robot on it, and with it being in that enclosed atmosphere as well, we're limited to parts of up to around about 1 meter in size on that. So those are the metal technologies and capabilities we have at NMIS.
No shortage of them then?
A few then. Yeah.
Okay. Grant, I've got another question which could come in there. It's a $64,000 question.
Okay.
And it's come in from George Campbell. Hi, George. And George is asking, his question is really around how manufacturing companies afford the investment and training. So there's an assumption in there of maybe some of the affordability about it. Can you, Grant, give us an insight into perceived affordability of 3D printing technology, and actually, I guess, the purpose of NMIS and AMBATS in helping to de-risk investment in technology introduction?
Absolutely. So what we're here to kind of set out and do is, as you say, de-risk that. So that could be working with us to create high fidelity prototypes. It could be trialing the manufacturing process and going away and doing some mechanical testing on it to make sure it is fit for purpose for what your application is. But what we will always do is consider, if you don't think that you have the investment to be able to go out and buy and train people on this, is we'll work with our network partners to understand what are the supply chain opportunities out there. So there is existing supply chain within Scotland on most of the technologies now, from companies like Whittaker Engineering, Glen Almond, both cover wire arc additive manufacturing. Metal powder bed, you have CA Models and Sterling, who have titanium and aluminium capabilities. Polymer companies such as AMA 3D and Bells Hill, Angus 3D Solutions, who actually have some metal capabilities as well up in Montrose. I might get in trouble for that one, might not be quite correct. And then you've got other companies such as Mage Control Systems, who've got Peak, Orthogonal Engineering up in Aberdeen as well, who've got Peak capabilities. And anything we can't find in Scotland, we'll most definitely be able to find in the UK, but also we've got lots of contacts within the EU as well. What we can do is give you as much help with the training as we can do as well. So things like the design, process, development, etc., all of these things, what that'll help you do is be able to ask the right questions of your supply chain partners, and if you are investing in the technology yourself, should be able to help you hit the ground running a little bit faster than you may have previously been able to do otherwise. Hope that answers the question.
George will no doubt come back to us. Thanks for that, Grant. Grant, would you describe sort of entry-level 3D printing as expensive?
No. So the way I normally quite like to think about things is 3D printing is your more entry level, and as things get more advanced, you then move up into additive manufacturing, proper serious manufacturing process. But your entry level 3D printing can be as little as £500–600. This can be really good for creating jigs, fixtures, prototypes. So start to think about fit and form. But obviously, as you invest in slightly more expensive machines, you'll be able to do more with them. So more high fidelity prototyping and manufacturing will be unlocked and enabled by some of these more expensive machines. Hope that answers the question.
Grant, I'll just add to that. It's what's always struck me with 3D printing is the ability to have componentry more available to you, more local to you, even printed on your own site. The ability to reduce cost of especially metal components, whilst at the same time offering the opportunity to print very complex sort of components. And given the fragility of global supply chains that we've all experienced in the last year, what a terrific way potentially to reduce the lead time for your supply chain. Yeah,
absolutely. So another way to kind of think about using additive manufacturing is we often say there's some circuit breakers to the rationale behind why you would do something. So if your component maybe at the moment in time costs £500, but you've got a large lead time on that, say 6 to 8 months, but you're offered a part that can be made by additive manufacturing that could be turned around in 3 weeks, but maybe cost £800–900. These are one of the reasons why you might think, right, okay, I can use additive manufacturing to unblock kind of blockages in your supply chain and lead times, etc.
Thanks, Grant. Grant's come back with, sorry, George has come back, just talking about getting into a little bit more detail about how accessible such technology is to people. The purpose of, George, if I may give you a little bit of input there, is that, as you may well know, through NMIS and Advanced Manufacturing Challenge Fund Innovation Hubs, Scottish Government and other sources have pumped a significant investment into the innovation ecosystem in Scotland, not just for 3D printing, but for a number of areas, all of which are designed to help de-risk innovation, de-risk investment, and to help design and specify purpose-built solutions for companies and take them through the process of introducing not only the technology, but building the business case to de-risk it for them, irrespective of the depth of your pockets or the ambition of the technology that you might be looking to introduce. So there's a terrific ecosystem sort of developing in and around us for that right now. In terms of your point regarding CapEx, we're seeing that day in, day out within the Manufacturing Advisory Service. Companies are coming out of the other side with COVID, having invested significant amounts of money in social distancing and additional staff, and also paying more through supply chain for ingredients and or just commodities coming through. There is no doubt that day-to-day costs are biting into CapEx budgets. So we are seeing that. So any help and assistance that the likes of the innovation centres can help provide on de-risking that's their purpose in life.
Yeah, absolutely. And what you can do within some of the support packages that we offer is we can set up mini projects where, as I say, we can look at prototyping, we can look at development, and if the technology that we've highlighted that suits your manufacturing challenge that we don't have at the National Manufacturing Institute of Scotland, we can work with some of the other catapult centres in the UK. And we can also work with supply chain partners, and some of this will be free of charge, and that cost is basically picked up by the investment that Ian is describing there, both by Scottish Government, Scottish Enterprise, the National Manufacturing Institute Scotland, and the EU funding that we have received.
Okay, Grant, I've got one further question for you. There's a lot of chat going on in the chat box, but I don't think any further questions. Feel free to drop them in, folks. You mentioned in your case studies a number of areas regarding medical device, sort of therapeutic devices. If I had a project proposal around kind of to manufacture a medical device, what's the linkages between yourselves at NMIS and AMBATS, along with the kind of Medical Manufacturing Device Innovation Centre? Who do I go to with my project, and/or do you all collaborate?
Yeah, so what we can do is work across the different AMCF projects, and not to complicate matters, there's also another one or two called the LCCF, which is the Low Carbon Challenge Fund. But what we can do is work across these projects to deliver the help and assistance that you need. So this specific example of medical devices, there is a AMCF project with the Heriot-Watt, Glasgow Uni, Edinburgh Uni, and RGU, which is a Medical Device Manufacturing Centre. And what we can do is we can run a project jointly between the two. What I would recommend, even if you know that additive manufacturing is going to be the manufacturing process that you want to use, the first port of call would definitely be MDMC and the team there. And then they'll be able to work with you to analyse exactly what your challenge is, and then they'll be able to bring us into the project at the appropriate time to be able to help and assist and use the expertise of the NMIS AM technologists.
Grant, thanks for that. And sadly, part of my duties is timekeeping today. And it appears that we're going to come towards the end of the workshop. Oh, there's one further question. I'm sure we can fit another question in. Yeah. Can I ask another question, please, Ian and Grant? Steel tooling for moulding companies is hugely expensive and normally results in long lead times and last-minute engineering changes. Never seen that. How much cost and lead time do we think that additive manufacturing can take out of this?
I don't want to give an exact number, but what we can do is there's a number of different ways you can look at this. So if it's an existing tooling, piece of tooling, that you do have and you're needing repaired quickly, there are a number of companies in the UK that I could signpost you to that would be delighted to look at this and do work with very quick lead times on these. But you can also use the technology to manufacture the die in the first, or die or mold in the first instance as well. So rather than being tied down to using something like H13 or D2 tool steel, because you're driven by cost as well as performance, you can still use tool steels to manufacture the bulk of your tool or mold, but then you can use additive manufacturing to then coat that tool in a high performance material such as Stellite 21, Stellite 6, Invar, these kind of materials that will give you that enhanced performance that'll make your tool last longer as well.
Grant, thank you for that. Recording is still going at the moment. At that point, folks, I will simply thank Grant and everyone at National Manufacturing Institute for Scotland and AMBATS for their input and fascinating insight into additive manufacturing, potential for a greener, lower costs, lower weight, more efficient way of producing components. And I thank you all for attending, and I would just like to wish you all the best for the rest of the conference, and hope you really enjoy the rest of the workshops and plenaries that we've got available to you. Thanks and goodbye, everybody.
Thank you. Cheers. Bye now.